Hello all and welcome back to this course on computer organization. So this being the last week, I think it's a very good idea for us to look at certain advanced concepts with which today's microprocessors actually work. We are not going to get into the details here. The questions and problems that are going to be asked in this course will not be based on this, but it is important for you to know that the basics that you learned in this course can be carried forward straight away to these advanced concepts and advanced microprocessors as well. Okay, so let's look at a few of these details. I will be alluding to some ideas mainly here, but it's up to you to go back and read more about this and understand it. So today, in microprocessors, right, there are a lot of other things which are done, right? We stopped with the discussion of a pipelined microprocessor. Basically, we wanted, a very small clock period, but a throughput of one instruction per cycle. Ideally, if there is no stalling or branch prediction and all, that would be the case in a pipeline microprocessor, but that is not sufficient to meet the compute requirement of today's workloads, right? So therefore people have been looking at deep pipelining, micro operations, branch prediction, superscalar processors, out of order processors, and register renaming, multi-threading, and multiprocessors, right? So what is deep pipelining? So we looked at a pipeline with 5 stages, right? But typically the number of stages, right? You can take a big combinational block, even like for example the ALU. If it has a multiply operation, you could take the big multiplier which has a very long critical path and break it into smaller combinational blocks by pipelining, right? Like that, it is common to do a pipelining stage of 10 to 20 stages. Of course, all of this is going to be limited by the pipelining hazards, and every time you add a flip-flop between two combinational blocks, remember that you add a TPCQ delay and a T setup, right? So for every flip-flop that you add, launch and capture, you're going to have a sequencing overhead of TPCQ plus T setup, right? Only the remaining part of the clock cycle is actually available for the combinational block to execute. Therefore, increasing the number of pipeline stages significantly is also not a good idea. Okay. Of course, there is a power and there is a cost. So if you look at what is plotted here, right, on the x-axis is basically number of pipeline stages. Obviously, we start minimum with 5, okay, based on the 5 stages of pipelining. Then you can do 6 to 12 stages. Every time you start, adding a flip-flop in between a combinational block by breaking the combinational block into multiple parts, right, the clock period will obviously start becoming smaller and smaller, right? Now, therefore, the clock period is bound to decrease with time, okay, with the number of stages, I'm sorry, right? And that's what you see in the black curve here, the black diamonds. It's, you see that the clock period, right, is dropping with the number of stages. On the other hand, the instruction time can actually, it will initially start dropping, okay, because ultimately it really matters how much time does it take for the instruction to finish, right? So there is a sequencing overhead that is going to kick in and all that, and of course your pipeline hazards, branch misprediction and all that, that will kick in, and therefore that average time can start going up after some time. So there seems to be an optimum where you might want to operate this microprocessor at, but this depends on your workload. Remember, we looked at the program execution time, and the program execution time depends on the number of instructions of each type, right? So it's perfectly okay to take a processor and actually fine tune it for a certain workload, because that's what it is going to see most of the time, right? So you might say that it's not optimal in one sense, but it may be optimal in another sense, right? So therefore that is also indeed possible, and therefore people have been exploring deep pipelining as an option for this thing. The other important thing is, right, remember in x86 we looked at all sorts of complex instructions, right? We said when you do call, basically it is going to call some address, right? You take the address, put it in the instruction pointer, then automatically this thing gets pushed. Okay, so let's actually look at this operation here, right? So if you look at the call instruction in x86, okay, address, right? So typically this is, you know, going to do the following, right? It is going to push the return address, right, onto stack, and then it is going to jump uh, to the address that you specify, the new address that you specify. It's actually going to go over there. That's what the call used to do, right? Now this, if you look at, if you want to just analyze what it would take to implement this instruction as an absolute instruction in the RISC-V processor, right? What you are trying to do, so this, by the way, okay, pushing onto stack again is, what is it going to do? It is going to basically subtract you know, ESP comma 4, okay, and then it is going to do a load word of the return address that we have, right? It's going to do it's going to write this address into the contents of ESP, right? So typically what would have to happen now is, you will have to move this data into some register, okay, EAX comma return address, right, sub ESP comma 4, okay, and then you will have to do load word, okay, into the memory location contents pointed to by this. So we are going to do EAX comma contents of ESP, right? So this is what you want, or if you want to do, you can also do load word EAX minus 4 of ESP first, and then you do subtract ESP comma 4, right? That's what is effectively going to happen. So this actually seems to be 4 instructions in one shot that are happening in the x86, and of course all of this is implementable and feasible and practically usable only in a multi-cycle processor, not in a single cycle processor, right? So in the multi-cycle processor, you are doing like 4 instructions. Now just think about, okay, what should you do if you are to do this in a RISC-V, right? It's a very complicated set of instructions that is going to be needed to implement, and therefore, and specifically when you go from multi-cycle to pipeline processor, it becomes even more complex, right? Because you know, it's not that the processor is idle till all these 4 instructions finish, no, right? There are a lot of things, every cycle, in every clock cycle, every single stage of the pipeline is doing something, right? There is no idle time ideally. So therefore, taking these multi-cycle ideas into pipeline process is not that easy, okay? And that is why the idea of, even in x86, in the CISC-like processor, you break complex instructions into smaller, micro instructions, and that is exactly what we have, we call as micro operations, right? So at runtime, complex instructions are decoded into one or more micro operations, and it is specifically used in CISC, okay, like x86, okay. So this is what we have here. The post increment operation is what we have shown here, but I also showed you the call example. That is something that can be very nicely implemented using the micro operation. So what happens is, you may write just one line in C, the CISC might just say, okay, call something, but internally it will generate those micro operations, and that is what gets pipelined one after the other, right? Now the other thing that has a very serious impact on the cycles per instruction, right? In the pipeline processor, we would have liked the cycles per instruction to be 1, but there is something that really takes it away from this value of 1 and increases it to more than 1, which is basically branch prediction. Of course, stalling is also one issue, but mostly branch prediction, you know, you have to flush out the last 2 instructions and all that stuff, right? So it would be good for the microprocessor to make an educated guess on whether the branch is likely to be taken or not. So basically you want to reduce the mispredictions on the branches, right? So for example, right, when you write a for loop for I equal to 0, I less than 10, I plus plus, most likely the backward branches are taken, right? For I equal to 0, I less than 10, I plus plus. So 10 times you're going through this loop, you are actually going to go back 9 times out of 10, right? So good idea, intuition is to consider the history and improve the guess. Okay, so you have to keep track of this somewhere. So you have to keep track of this state, and good prediction obviously reduces the fraction of branches requiring a flush. Okay, so like I said, ideal pipeline processor CPI is equal to exactly 1, right? If there was no stalling or branch misprediction. Branch misprediction obviously increases CPI. So you can do this branch prediction in 2 different ways. You can do either static branch prediction, okay, that is you check the direction of the branch whether you're going forward or backward, right? And if it is backward, then you predict that it is taken, right? That's the key point. The prediction says, okay, if you are going through in the backward thing, then you assume that it's likely to be taken, else the prediction is not taken, right? On the other hand, so this is just, okay, you look at the C code and, oh, there's a for loop, I will do this, right? Now what we are saying is dynamic branch prediction, right? So you keep history of last several hundred or thousands of branches in a branch target buffer, okay? Record the branch destination, whether the branch was taken. Use this information to sort of improve your branch prediction, right? So you can do multiple things. You can have just 1 bit for branch prediction or 2 bit for branch prediction. Okay, so let's look at this example. For I equal to 0, I less than 10, I equal to I plus 1, sum equal to sum plus I. Okay, initially we are basically saying you know, T0 is going to be initialized to 10. So that's why you see this instruction here, add I S1 0 0, right? You are just initializing the sum to be 0. Okay, then you are basically going to say add I S0 comma 0, which is basically the variable that I am going to assign to I, right? This is the I equal to 0 that is happening there. That's a register that I am using, by the way, and add I T0 comma 0 comma 10, right? I am going to say T0 is 10. Now that's where I am storing this number. Okay, so how do you do it in RISC? You would basically just say branch or greater than or equal to of S0 T0 to done. Okay, what does this statement do? It is going to do S0 minus T0, right? And check if it is greater than or equal to. If it is greater than or equal to, it means you are done. Okay, and therefore you will just finish and come out. Otherwise, what are you going to do? You are going to do sum equal to sum plus I and I equal to I plus 1. So that is what is happening here. Add S0, S1 comma S1 comma S0, right? S0 is where I is. So initially I started with 0, the value 0. Then you added sum equal to sum plus I, okay? And that is being kept track in S1 register. Then you say add I S0 comma S0 comma 1, okay? So basically what's going to happen is the I will become I plus 1 through this S0 register, and then you say jump to the for location. This is where we are going to jump, okay? So this is basically an unconditional jump, right? Whereas this one is a conditional jump. Now the point is the conditional jump is sort of taken 9. So what happens is the jump is going to cause the program counter to jump here, right? Whereas the prefetching would have fetched this instruction, correct? So therefore what is going to happen is 9 out of 10 times the branch is not going to be taken here, right? And therefore you are just going to proceed like that. So that is a good thing, correct? So the 1-bit branch predictor basically remembers whether the branch was taken last time and does the same thing, okay. And so what will happen is it will mispredict the first and last branch of the loop, that's all. So first time it doesn't know because the branch was not, never had to be taken. So what you do is the first time the branch is not taken, second time, third time, fourth time, it will just continue to do exactly that. And here when you come here, again first time it takes the branch. So it is just unconditionally going to do that, and therefore you always take the branch 10 times, and you, of course, the last time when you come here you will make the mistake, but that's absolutely okay, because you are doing only one misprediction as opposed to 9 mispredictions, right? So like that you can also do a 2-bit branch predictor, right?